Hello everyone, my name is Mark Shipman and today I'm going to talk about anomaly detection. I have 25 years of modeling experience. I studied machine learning at Carnegie Mellon University and financial engineering at Columbia University. So my approach for anomaly detection will use machine learning. Machine learning is a process whereby you use historical data to train a model and then you use the trained model to make predictions for other data. So what kind of data would we use to train a model? So in this proof of concept, we start with electricity being delivered to a consumer. That electricity is measured by a meter, and then we collect that historical data about those customers. We also have other data about those consumers. It could be demographic data, it could be information about the building, it could be information about the neighborhood, and I'll talk more about the data later. Once we have all that historical data, once we have the data set ready, then we can train a model to estimate the expected meter reading for a consumer and then compare that to the actual meter reading and create a conformity measure, the ratio of the actual meter reading to the expected meter reading. When this ratio is lower, that means that the meter reading is lower than expected. And then when we have a conformity measure for every consumer, we can look at the distribution of all the conformity measures. And some consumers will be at the lower end of that distribution. Those consumers at the lower end of that distribution will have an unusually low actual reader reading when compared to their expected meter reading. So now I want to talk a little bit more about the data that we use to build this model. So first there's the response variable, what it is we're trying to predict, and that's usage. So that could be kilowatt hours, it could be kilowatt hours per square foot, or BTUs. There's data about the building, and that affects usage, size, construction, type, age of building. These are variables that affect how much electricity is consumed by a consumer. Then there's demographic variables. It could be income, number of family members, number of cars, whether or not they work from home. Some of this data may not seem like it directly affects how much electricity is consumed, but it could be a proxy variable for something else. And then there's exogenous variables such as weather or economic data. So weather, for example, in colder months, you're going to see people use more electricity, and in better economic times, you might see people also consume more electricity as they have more disposable income. So the city of Chicago has a data set that it's made publicly available that has electricity usage. The electricity usage is aggregated by the census block. Also in that data is the building type and some other information about the building. So now what I want to do is I want to connect the data from the City of Chicago about usage, and I want to connect that to other data sources. So the U.S. Census has data on neighborhood demographics. The Bureau of Labor Statistics has data about employment by industry. There's also spending by type from the Bureau of Economic Analysis, which also has data about the overall economy. And the Internal Revenue Service has data about income. And the NOAA also has data about weather for temperature and other related weather events that would be relevant to electricity usage. And all this data is free. So after combining that data and training a model, here is a model importance graph. So the model I used was a gradient boosting model, and the response variable here was defined as kilowatt hours per square foot, and in this case it was greater than 5. There could be other cutoffs such as greater than 10 or greater than 15, and you could also have a model that just estimates the kilowatt hours per square foot. There's a particular reason why I chose this model for this demonstration is because it had better accuracy, it had better performance. And you can see the most important variable is the building subtype, and that has to do with whether it's commercial or a multifamily unit, for example. Then there's other variables on there about the size of the building, and there towards the bottom you see also some of that census data. So in this particular proof of concept, the only two data sources I use were the City of Chicago and the U.S. Census. Those other data sources could be considered, but were out of scope for the purposes of this proof of concept. So this is a precision recall curve. A model has various sensitivities. So you can be more or less sensitive. And what that means is it chooses to label more or less of the accounts as anomalous. So for different levels of sensitivity, the model has different levels of accuracy and different levels of recall. So precision is basically accuracy, how many of the estimates were correct, and recall is how many of those that were anomalous did the model actually include above that sensitivity point. So the way you would read this is you look at the X label, and this corresponds to different sensitivity points. So for example, at a particular point where it says 0.6, that's a sensitivity point. That means 60% of the anomalous accounts were labeled as anomalous by the model. And then you look at this corresponding point on the y-axis, which is about 30%, and that means that the model was about 30% accurate at that point for that level of sensitivity. So obviously, as you go further to the left, the model is more accurate, but it's choosing less and less of the actual anomalous accounts. So this is a way you look at a model to tell how well does the model perform, and also it helps you understand where to set a level of sensitivity so that you can come up with a way to use the model. So using the output of the model, I looked at actual examples of buildings that were labeled as anomalous. So in this case, this building was labeled as anomalous with an expected 85% accuracy. And this census block, and here's a picture of a building in that census block, and here's a picture of the meter from that building. And here it looks old, which doesn't necessarily mean fraud, but it's an example of a meter that might be less reliable or easier to tamper with. So in this example, this is another census block that was also labeled as anomalous. And here you can see that the electricity meter is actually being covered by something, so it might actually be interfered with. And so that may be another reason why a building might have an unusual meter reading. This concludes my presentation. Thank you for watching.